Folks, let's get started. It's my pleasure to welcome Professor Mani Ghaffari, today's speaker for our CNRE Winter seminar series. So Mani is faculty in the Naval Architecture and Marine Engineering Department, as well as the Department of Robotics here at the University of Michigan. And his research is in the theory and application of robotics and autonomous systems. And he's an expert in developing efficient generalizable algorithms for robot autonomy operating in unstructured, dynamic, and uncertain environments. He's a recipient of the 2021 Amazon Research Prize, as well as the Best Paper Award for his work. So thank you again, Mani, for taking the time to speak to us, and look forward to your talk.
Thank you for inviting me. It's a great pleasure to be here. And I'll be very glad to share my work with you. So I'm, as the nice introduction said, assistant professor in naval architecture and marine robotics in joint appointment robotics. So much of my work focuses on robotics ranging from theory to field robotics, and also includes marine robotics as part of it. So sometimes the results, robot is not in the water, but a lot of algorithms sort of carry over to different domains. So a lot of motivation is that, you know, the world is full of uncertainty. It's very difficult to structure everything for the robot and autonomous system. That always sort of poses an ever-changing challenge for robots. Natural disaster is obviously a big motivation for search and rescue. And a lot of times these are coastal environments because hurricanes, floods. So it's a mix of land, water, air. So often, you know, we need different mode of locomotion and modalities. Another reason is there's a big push for AI and self-driving cars. It's the workforce problem, because a lot of countries are facing population collapse, and that and some of them are developing countries, even though they need more people to build the country. They're either immigrating to countries like US, or they just don't have the young workforce to build the country anymore. So that puts a lot of pressure on maybe building a autonomous system that can take care of our old parents. And my parents are in a different country. If I want to pay people to do something, those people might not be around. So I need robots to actually, at least, you know, clean the house, do something in the kitchen. And those are as hard as, it turned out those are as hard as sending a robot underwater. Give credit to yourself, be cleaning the kitchen. And another motivation, generally for the AI system, is to interact with humans. This ranges from, you know, a lot of, again, applications. A lot of research is funded by Navy in this area. Naval applications are not separate. You want to have an autonomous system, but these robots are going to interact with people. And from, you know, loneliness to, you know, entertainment, art, museum, disaster, but also, you know, military applications and a lot of, you know, urban applications. So collaboration with humans and robots are very important. So in that sense, a lot of my work is about explainable algorithms that are not necessarily end-to-end without transparency, because if the robot ever wants to have shared understanding of the environment with humans, that basically representation of what the robot is seeing and understanding, and being able to visualize and show that to humans will be very valuable. So the unique approach that we take in my lab hinges on computational symmetry. And the reason is that because you guys are sort of physics adjacent, so a lot of you have good physical knowledge. So in physics, there's a lot of interest in the symmetries of systems, because once you understand the symmetries, we can strip all the unnecessary elements and work with the bare necessary representation of the system. Plus, that will generalize to different settings, regardless of, for example, choice of coordinates and a particular setup. And that sort of shows up in artificial intelligence and robotics as well. So it's a good unifying language with mathematical physics, engineering, by inspiration, and robots. The computational approach is that because we no longer they solve differential equation by hand. There are maybe some 16 equations we can do, and that fantasy that we're going to solve everything by hand is gone a long time ago. So we solve large, linear systems by computers, and everything is on CPU. So together, this sort of opens up an opportunity to take computational approach to symmetry and calculation. These are sort of computational algorithms that are aware of the structure of the problem and can leverage intrinsic properties of the problem to generalize and work more efficiently. And the reason again behind symmetry generalization, because the kind limitation of the AI systems that they do not generalize. And if you want to run a PCA, what sort of I focus on one direction, independent direction is computational symmetry. Some of the work are the theory side, but we try to sort of turn them into useful algorithms to show people that they have merit. Learning and optimization obviously is a big factor that can range from scientific computing to deep learning and a lot of old and new problems that we use. So optimization and machine learning at this point, it's hard to draw a boundary. All the optimization people are publishing in machine learning venues. And another problem that we have is that to build systems, which is something able architects basically become good at, is that we need new principles. It's not very easy to put together a common system to have so many capabilities and still be consistent, and whenever we want to add something, we can add to that. And system integration is very challenging. It's very time consuming to put a robot together and then take it out to experiments. It takes a lot of time from students, and often it's one time off. People do it, and then next time, say in a month, we want to do it again, it's all over again. Maybe it's a little bit of it reusable, some of the algorithms and libraries, but a lot of tuning, a lot of work. So that's very hard. So I'm going to stay in this XY plane today. The third direction will be for the future. So now to look into the symmetry, it can get very difficult very quickly. Look at the literature of math and physics. But the next easy thing that sort of after Euclidean space that we could learn, we could do something useful with it, is basically matrix legals. That would be the next easy geometric object that generalizes the Euclidean space, and notably, for example, includes 3D rotation. So a lot of autonomous system, robotic system undergo 3D rotation and translation. And 3D rotation sort of is a canonical example of a matrix. And these groups are very nice objects. They're homogeneous spaces and symmetric. You can model, for example, rigid body system as special Euclidean group of dimension 3. Homography group in computer vision, when you do change of perspective, planar objects remain planar. That's called a special linear group. And generally speaking, the dynamics and kinematics of robotic system articulated system can be modeled using sort of direct product of these three groups. This is much easier to do for rigid system. If you want to do it for fluid system, it becomes infinite dimensional. Those are typically much harder. So I don't work on that. If you want to take this approach on fluid system, we can talk about the algebra of the fluid system, and those are typically infinite dimensional. Now, a basic example that whether the robot is a land robot or a marine robot or drone is that the robot needs to know how fast it's going and where it is located. We need to know, to expect some reference frame, what is the speed of the robot, what is position, what is its pre-orientation. And typically, if we want to think of this as an observer that is giving us these quantities, it needs to be high frequency because there's a controller on the robot that commands the actuation to do whatever maneuver we want to do. And that controller relies on high frequency velocity feedback to regulate the error. So there's a state estimator and controller, and often they work in projection in a high frequency loop. And the reason we need observer because something like robots whose velocity are not directly observable. There's no sensor that you put on the robot gives you these quantities. You can have GPS, for example, to give you position. It's military grade, it will be accurate. Or if you can use RTK GPS, it will be accurate. But even those will only give you position. It's not going to give you high frequency, velocity, and orientation of the robot. But I'll tell you, a lot of applications we are interested in are GPS denied environment, underground, mine, underwater, different planets, for example, or even congested urban environments. GPS is not very reliable. But if it's available, of course, we can also use that.
Mani, when you say high frequency, high with respect to what?
High frequency is something like 2000 hertz, for example. This algorithm is running, say, 1000 hertz or 2000 hertz.
Is what you mean by nice.
High frequency. Okay. It's the bandwidth of the signal that you read from sensors and then you process. So as part of that, the work we did just in my PhD student, former PhD student, he graduated last December, is we built a library that uses a symmetry preserving observer that works on all sorts of robots. It could be Lego robot, wheeled robot, some indoor robots, full-size army vehicle, and also marine robots. And the symmetry shows up here in the sense that for linear systems, it's possible that sort of study the evolution of the error in such system independent of what's the actual state estimate. Without knowing the true value of the state, if you derive the aerodynamics for linear systems, typically that does not depend on how far we are. That's why we can get classical results like for linear system, we can have convergent observer and controller like LQR methods that using matrix algebra. So those classical results in optimal control are very good, but the problems that we want to solve are nonlinear. However, they're nonlinear, but we can still model them on matrix groups. So they can be modeled on the next easy geometric space. Very nice results from Baru and Bonabel and formalizes a property called group affine property. So we can ask that what's the analogous linearity for the matrix group, a group of matrices that resembles that linear system. And it turned out that you can prove a theorem that if you want to get an aerodynamics for a dynamical system that doesn't depend on the true value that you're trying to estimate, it needs to satisfy that property. Looks weird, you wouldn't come up with it, but you start backward, start from the state-independent aerodynamics, and it turns out that's the group affine property for continuous time process. So you have a process model for a dynamical system, this model base. You check both sides. If it satisfies, it's group affine. And the way we work, we are working with a matrix group, so we don't add and subtract because we fall out of the group. We respect the group operation, which is matrix multiplication. We get to define error from left or right. Your estimate multiplied by the inverse of the true state, or from the left side, the inverse of the true state multiplied by the state estimate. The reason it's invariant is that if you transform both of these terms, the error from the left side or right side, depending on the definition, they get canceled because of inversion. The order of the matrix multiplication will shift terms, and then the error gets canceled. So what does it mean geometrically is that the definition of the error, it does not depends on where your pose is, where you the object could be here or here. Doesn't matter. It's about the relative distance between the true trajectory and our current trajectory. That's a result of homogeneity of these spaces because they're homogeneous. Everywhere is the same. So all we need to know is the relatively where is the ground truth?
No, this is true for any f.
Any process model, continuous process model, if it satisfies its property is group affine, that means that we can model its the evolution of the error dynamics with respect to some true value of x that we don't know, independent of that. So for robot motion, that's very sort of useful because we can evolve the error sort of covariance uncertainty very accurately regardless of what is the true value. Classical results relies on Jacobian linearization for error propagation, right? You can validate the Jacobian at the current estimate. If it's wrong, that creates a positive feedback loop. That was the problem for me. Now, I do not know the extension of this for the fluid system, but
It could, if this were even approximated, then it would still have be incredibly useful. So you can think along this way, I think.
If you think of particles, right, this particle could be modeled like this, and then
Yeah.
you can have error, state independent error propagation for trajectory of the particle. Correct. So that's what there's a history of the symmetry preserving observer in the literature, but this particular result for 2015 and 17 of several publications from France. Right? And error remains invariant because it's all about relativity. How you move, not very well. And you could build a Kalman filter. It's a famous recursive state estimation method that if you take that property of affine property and definition of the error, you can build a nonlinear filter for estimating, for example, rotation and rigid body distance. That it gives you constant Jacobian. It's not linear, but linearization is exact. So the direction that you sort of move is always the same, because everywhere is the same degree. So that was very surprising. G is the gravity, so you assume it's fixed, and that's because the measurement Jacobian is constant. I'm not going to a lot of details here, but this week, for example, I taught this filter in mobile robotics course in 2 lectures. So we teach it in Michigan, one of the only universities that we teach this program. Watch this video. Talk less, you can see some robots moving. There's a library. There are a lot of options into it. For example, if you have a cheap gyroscope and you want to make it expensive, you can use 2 cheap gyroscope or use kinematics of the robot to improve its quality. Private good Amazon robotics, they for Astro robot, they wanted to use cheap sensors obviously to mass produce the robot. So we had to solve this problem. And it works. So here, for example, the robot is moving, in different trains and different speed, and what we want to do, we want to estimate is the trajectory and velocity, but we're just visualizing the trajectory. This is outside of the robotics building. And we don't know the ground truth because it's sort of in the wild. There's no motion capture or particular ground truthing systems. But what we do in the end, we overlay the trajectory on the satellite. You would see that it's correct. We know what path we want. This is a mini cheetah robot from MIT. The lab was one of these from Weekend lab. So this is the path we walk, and qualitatively you can see that it's correct. And another project with Ground Vehicle Center, and the Army, for a good reason, was very interested in this filter. They wanted to know what's the limit. And I just told them off the top of my head, I don't know, 1 kilometer. And they said, no way. So with one inertial measurement unit that you have in your phone, the shaft encoder, no vision, right? We want to track with the accuracy of almost like RTK GPS for several kilometers. And it turned out we can't do that. So we collected data in Pittsburgh. This is the paintball facility for Neo Robotics collaborators. We collected the data, and then there's an RTK GPS, which is very accurate trajectory of the vehicle. And despite all these problems or vehicle slipping and sliding and getting stuck, we're not modeling any of these things. And as I say, the robot is blind. So it's just inertial sensing, accelerometer and gyro data for angular velocity, and then rotation of the wheels. That's all we need.
All four of them? All four wheels, 4 encoders?
No, I think you could, but in this case, I think it's just back or front, one of them. That's what was available to us.
So if there's a significant slippage, will it affect the?
There is, but we're not modeling. We're fine. It's working. We don't touch it. First rule of engineering.
Sorry, Mani, can you repeat that again? What do you have on the vehicle?
One IMU that we have in the phone, right? Three-axis gyro, and which gives angular velocity, and three-axis accelerometer, which gives acceleration. That we use that to predict the motion, and then we use cat encoder, which measures the rotation of the wheel, and we convert that using kinematics of the vehicle to the body velocity of the vehicle. Basically, we know the forward velocity of the vehicle from a downside. Right? And with that, we can get that trajectory that is similar to high accuracy techniques.
I see.
And then, so there's no particular limit. We also did it on this robot on campus. There's the limit. My student collected data as much as battery allowed. 50 minutes, I think. 55 minutes. Very cold as well. You have to do it. The limit here is basically the robot battery collecting data, so I think we can go much farther. And then we go around campus, and this is just the tracking. So this is a very interesting technology going. Navy as well. This the reckoning was an old problem in submarines. That's how they navigated the report part. This is a simulation, but right now we have a new surface robot in the lab. That robot we use because it's on the surface. We use GPS, and we have good results on that as well. Sort of a technology now. This one is for underwater. You can still use IMU because IMU is a good idea because in aerospace, sort of they have this idea of calling it strap down. You strap the IMU and bypass the vehicle dynamics. You don't need to model the vehicle dynamics for tracking. For underwater, we use the Doppler velocity. It's a sensor that uses Doppler effect to get the ground reference velocity. So that, we did a lot of work and the filtering side, and so the theory wasn't from us, it wasn't from Michigan. It's from France. We just made them famous by putting it on a lot of robots. So I talked to the student that we should do the dual version of it. If you have this common filter, which is the linear quadratic estimation, and the dual is linear quadratic regulator for control. There must be a dual. Let's do the dual version. Which then led to tracking controller and link group using same idea of the symmetry. Now I want to build, say, model predictive control. I want to control whatever robot that I have, and I want convergence regardless of this is the desired trajectory, and then you start from here. The goal is to track this reference, right? If you set a reference and then you want to track that. This is the problem of tracking controller. But I want convergence regardless of how far these two are. I want to converge and track. Okay, so with the lesson we learned there, we formulated a problem like this because for every matrix group you have this kinematic equation of motion. It's known as reconstruction equation. The time derivative of your matrix equals the matrix times your velocity, which is sort of in the tangent space in the identity. And So this is a kinematic equation of motion of the desired trajectory. And we have our own kinematic motion of the robot itself. We can define the error using matrix multiplication and then take time derivative of that. We can get a nonlinear aerodynamic, how this error of the tracking the rigid body force is evolving. And this part is just the velocity. This is the adjoint map. You can think of it as matrix similarities, doing change of basis, because these two velocities of where I am and where I want to be are not in the same frame of reference. You have to do change of basis to bring these two vectors in the common frame. That map is just doing that automatically. Now, one problem is that people typically write down generalized coordinates and use Euler Lagrange to write down the equation of motion using variational methods. And that doesn't work very well because it's not linear and it doesn't match the formalism. In sort of symmetry in mechanics, which was sort of very popularized or studied a lot by Marsden, Abraham and Marsden, they have a book. And Tony Polak as well, in the math department here, I collaborated. So the way they model equation of motion, they use this exponential coordinates of this matrix D group, which gives the natural coordinates to write down your equation of motion instead of generalized coordinates. And that will give you the dynamics of your system in the Lie algebra. It can be done generally for any dynamical system. But for the rigid body is particularly nice and finite dimensional. This will be a 6-dimensional equation known as Euler-Poincare equation. Poincare is studied in the So as you see, this is a second-order equation, but only it does not depend on the pose, but only on the time derivative of the velocity and the velocity itself, which has a nonlinear. For rotation only, you might be familiar with the Euler equations for a rotating body. I omega dot equals omega cross I omega plus 4, right? So that this will generalize it to twist. You have linear velocity and angular velocity simultaneously. This is for a special repeating group of dimension 3. This part of it is not linear, but it's fine. We can linearize it. And so we have the dynamics as sort of an affine equation. Another thing we can do for these matrix groups are sort of also known as linear exponential groups because you can every matrix is a matrix exponential of some velocity in the Lie algebra, in the tangent space. And that sort of makes it very nice. We can always go to the exponential coordinates, which is a vector space. This space is nonlinear. It's very difficult to solve nonlinear programming here. So I go to the vector space. When we linearize, we get the sort of linearized aerodynamics in the tangent space. That, as you see, it doesn't depend on the configuration stage. This X values here. So again, I want to build a tracking controller, and I know the aerodynamics, and the aerodynamics does not depend on where I am. That's as good as it gets, right?
So if I were thinking of like the fluid equations or something, a system where you're evolving the velocities, you don't want the linearization to depend upon the current velocity. That's what you mean. When you say it doesn't depend on configuration state. If I want to go from n to n plus 1, I shouldn't linearize about n.
No. We linearize, we center it around the desired value, but then the way we sort of derive the aerodynamics, it becomes state independent, right? The particle basically is a state independent. You can simulate the movement of the particle. I mean, we can do a lot, right? We can do error propagation, we can regulate the error. This particular application. So I think the lesson will repeat. You want to do something, some modeling of dynamical system. Somehow you are dealing with this matrix group, rotation translation. You think of a coordinate frame, right? You can always get some type of results. Okay, so with this, we can put together quadratic program, quadratic loss functions, and linear affine constraints, which is convex. So previously we wanted to solve model predictive control, the optimization. Here is after discretization. You have to solve a nonlinear program. Now it's a convex QP, which is very efficient to solve it at a very high frequency using off-the-shelf solvers. So this is just we state is the error and twist my velocity, and then I define the output. Just building error system to put together MPC, and I have my terminal cost and the running cost and the constraint in the dynamics, and then possibly you have some constraints on the torque and input. You can include all those inequality constraints. So we had that, and we tried this control on legged robot, and then I had a postdoc Jumbo 2 years ago. Now it's back in Korea. I told them that I really wanted to work on a surface robot for marine robots, and that's what we did. So I don't. So the difference is that if the robot is sort of in the body of water, that equation of motion will not be as simple as this one, because the mass and inertia will change with the water, right? And there's hydrodynamic force. But that's still, I think it wasn't a big deal, because from handbooks you can sort of get how the mass and inertia will change. The hydrodynamic force can be modeled using damping matrix times this velocity, right? In the exponential coordinate, it ends up being a linear model again. So the whole equation of motion of vessel can be also written like this, and that's what we did. That was the new part of the paper. Before that, there's a Parsons version of the dynamics. He also models them in the body frame, but he uses Euler angles. Sort of the old-fashioned way of writing the dynamics, which won't be compatible with this symmetry preserving. So anyway, so this this letters paper is a short paper. It models the dynamics, and we made some simulation. Now we're implementing it on the surface robot to run it. Before we test it in MHL curves to go straight and come back, see what happens. But what happens is that this is the mathematical simulation. So the nonlinear MPC has access to the Oracle model. It's expected to perform better. So we have nonlinear MPC, the simplified nonlinear MPC when the model is simplified, and then there is this convex MPC that we propose. So all of them can track, and the error of our method is a little higher, but the error is really not a lot. 10 centimeters for a vessel is not a significant error when you want to track in water. But the good part is that it is 10 times faster. The critical aspects of model predictive control is that we predict, for some number of horizons in the future. That's its power. And then we do receding horizon control. That means we predict for 100 or 1,000 whatever steps in the future. I only take the first action, I apply it, and then throw away the rest. The next time is that I repeat this. So receding horizon control. So I plan for a long horizon, but I only take the first action. This allows for repeated correction of the error in prediction, because the more you go in the future, the error obviously will grow because these models are approximations of the reality. But the problem is that increasing that horizon is extremely expensive. For example, self-driving cars, that's the problem. You want to increase that horizon because you want to predict everything, if people can jump in front of the car or not. But it's expensive, then that it won't be real time. It's not linear. But if it's 10 times faster, that means you can increase that horizon, for example. That was the maybe serendipity out of it.
Why is the error higher? It's not clear you made any assumptions to develop your system.
Why is that though?
No, why that behavior? Why is the error higher?
Our dynamics is different from what we simulate. So
Oh,
that's my guess is if we do a physics-based simulation or in real world, maybe the gap is not as much.
I see.
Yeah. I would say the nonlinear MPC has access to privileged information because the dynamics that we simulate the robot.
It's in the system. I see.
Yeah, our reality is in perfect match with the model of the nonlinear MPC. So I guess it's the toughest baseline.
Hmm.
So this gives sort of a convex MPC for all robots virtually. So that was a very happy outcome out of looking into the dual problem of that. We can do multi-body systems. In this context, we haven't done. So next work I also did some work on geometric deep learning. Now, no escape from neural networks. So these classical methods are really good, and still we need them for robots because even though people don't talk about them, somewhere deep down in the robot they're running. When you see a robot, they tell you reinforcement learning is doing something, probably NPC somewhere down there, or they do joint control or something. It's not just pure what we see. But they're increasingly is getting close to design to methods. But one aspect that I work on is that to bring that knowledge that we have from classical methods outside of GPU and parallel processing into designing the network itself. So two approaches. One is physics informed. Design a loss function. Loss function will sort of inform your network of some physical property. That has been applied a lot in other PPE, for example. You use your equation of motion as a loss function. Now that inherently is not able to generalize because the network is not built to sort of respect the constraints by construction. Right? It's just that it will memorize as much as possible during training. So this approach is correct by construction. So you're probably familiar with MLP, multi-layer perceptron. You have a bunch of inputs, and then these inputs come in. There's a linear model plus bias. They go to activation for nonlinearity, and then this keeps going to build a multi-layer perceptron network, which is a universal approximator on some assumptions of any function. These nonlinearities in neural networks are scalar functions, often for a loop, rectified linear loop. So there was like a few years ago, what they did is say, well, why won't we making them vectors? And that was a good idea. So that made it SO3 equivariant. That means if you rotate your input, your features will rotate in the same way. So now you have a representation that transforms in the same way, the predictable way with your input. This is very useful because, for example, if you rotate your whole setup, the network is agnostic of that.
Yeah.
Rotate the lab frame, it doesn't matter. You get the same result. So this is very useful. For example, you want to say record the trajectory of the drone to learn the dynamics to system ID. Theoretically, one frame should be enough. You don't, and it doesn't matter where you install your camera.
And scaling also, right? Dilation and this and that will also be built in.
So the challenge is that building this equivariance property for different groups. For rotation, it turns out to be pretty easy. Rigid body transformation is also easy. So I've been looking into projected spaces for cameras. That one is difficult. It's not very easy. Scaling is also possible, but doing it up to standard that I like is also not very easy. And the reason is that what we did is that we now think of every node instead of a scalar as a group or category. Now suddenly the whole network becomes a geometric object, and in particular a Lie group. So now think of this hero as a vector space, a Lie algebra. Virtually you could model anything. Write down the Lie algebra of the 3D model. But we have to build it. And just implement it like this. So we need a nonlinearity. Obviously it's a vector space, you can always have the linear model, and that's fine. But if every layer is linear, the network will collapse to a linear model. The power of neural network is having those nonlinearities. The natural nonlinearity that come with Lie algebra is something called killing forms, trace form. And in particular case of say rotation, this trace form will lead to the dot product that we know. You can get a dot product out of it. Not for every group, but if the group is compact, this will give this is negative definite and will give a positive definite. Negative of it will give a positive definite dot product. Then we work with matrices in this instead of vector, we write it as a trace. Okay. And the good property of this is that it is conjugation equivariant. It commutes with conjugation property. And conjugation is the similarity transformation for matrices, change of basis. So the whole network will be will commute with change of basis. That's the promise. Okay. F is the whole network, and G is the group transformation, say rotation, and X is the vector field in the say angular velocity. But here, things that we can design. You can design a linear model. Bias will break the equivariance. So this is just linear, not affine. You can design the algebraic ReLU like this. You need to come up with a rule to reject or accept. So this works in practice. Although this is not a metric, or because it's not the case that always it will give you a dot product. It won't be necessarily a metric to measure distance, but that it turns out that's not necessary. You can just say if it's less than 0, you reject it. If not, you pass the signal plus this invariant code won't affect it, times the input and some linear part to make it different to the learnable weights, right? U is the learnable weight of the network. So that whole thing becomes equivariant. So to build a equivariant nonlinearity, you would need an invariant, basically, activation with respect to that transformation. Another cool thing is that you can use Lie bracket as a nonlinear. There's a famous work, resonance, residual network, which then people, study that, okay, that's just Euler integration. You could obviously do better with RK4, other things, right? This is a lot like that, but it uses intrinsic properties of Lie algebra. You have this Lie bracket, which you can think of it as Lie derivative. I'm taking the signal and adding a delta to it. So that sort of creates a residual layer for the network, but it is nonlinear. So this is a new type of nonlinearity that sort of wasn't known to before this book. Hopefully, you want to build an invariant features, you can stack these killing forms and you can build invariant features. That's very easy. So anyway, so now we can build a neural network that sort of operates in the Lie algebra by construction. Now, one limitation is that the input must be in the Lie algebra. That's the limitation. So one example, this famous problem known as BCH, Baker-Campbell series. Basically, you have the exponential of two matrices. You want to know what is Z, because it won't be x plus y unless x and y commute. Multiply them and change order. The solution is that it's an infinite series in the Lie algebra with nested brackets. So, no closed form solution for most groups. Now, we try to learn that BCH using a network. That I give the network x and y, it will just spit out Z immediately, right? If you do it with MLP, and if you do it on the training set, you have enough data, obviously MLP to learn But it won't generalize. If you now rotate the input, the error will increase because it hasn't seen those new inputs. This was another baseline that's also SO3 equivariant, rotation equivariant, but it doesn't have the bracket layer and the features that we have. So we can almost get numerical zero on single precision almost. And the error is the same whether you rotate the input or not. The network is completely agnostic of transformation index. That was an interesting observation. And then next problem is that we want to learn, say, dynamics. Now I want to learn that for your Poincare equation, in this case for rotation, using that network. So I use this in, I have a MIRI project from Air Force. I was presenting this, and then the program manager told me, pick the most non-rigid object for rigid body rotation. Because this is a space station, deforming and it's not rigid. But that's what we did. So the framework we're going to build is something that's called neural ODE. I think we have with it. If not, it's a very useful tool for learning dynamical system and vector field. It's a continuous step, basically, network. So what we do is that we have a neural network. Neural network is learning the vector field, and then there's an off-the-shelf ODE solver that is integrating it. And then we train it. This is outside of the network. And then we train this in a way that we learn this vector field, and as we integrate, sort of it matches the ground truth. Okay. This became a very popular idea and turned out to be a very good idea. Now we replace MLP with our network. It becomes equivariant neural ODE for NED algebra. And when you learn the dynamics, it matches sort of the ground truth. You can learn the body dynamics perfectly. And then we do change of frame. We learn the dynamics. Now let's do change of frame on the input for the sort of the velocity. MLP error sort of increases a lot, but also increases as you go forward in time. But it's very interesting that the numbers are exactly the same whether you rotate the frame or not. That makes it very robust to transformation.
So, do you have your charger?
Maybe.
Good call.
A few more minutes. This is just an example. Now, it doesn't have to be just rotation. This is a spatial linear group. All the 3x3 matrices with the determinant of 1. But it doesn't have to be orthogonal. So now we allow stretch and shear. The object can shear and stretch, but the volume is preserved. That would be SL2. You can imagine a softball that sort of squishes and stretches. It threw in a crazy function, same story. So it learns, and if you change a frame, it does not matter. Another experiment we did is that you have this platonic shapes, and then you have a camera, and then you want to classify which shape you're seeing, despite the fact that these are transformed in 3D. We rotate them, but then that will result in a change of perspective. And I guess the lesson is very consistent. It's very robust to change of frame. If you rotate it, you see MLP, the performance drops a lot, and that's the reason they don't generalize. The performance almost remains the same. So this gives hope that if we build in some structure, then we can generalize a lot of it. Basically, you model the whole class of problems instead of a single problem. That's a much better approach. Now, I want to spend too much time on this, but that lesson of symmetry, we also have a series of work in perception and slant, which is the problem of you want to reconstruct the scene using some point clouds or images, and you want to localize yourself simultaneously, simultaneous localization and mapping. And so what I sort of worked on in my lab in this is that previously people used to, think of these point clouds that you collect using sensors like LiDAR, and obviously independent measurements, and then you have maybe another set of points as you move, and then you want to register. So the registration problem will allow us to bring them in the common frame, and then you can reconstruct and build a map. You can see this room, for example, as this. But this didn't feel right, so this is the work I started doing since I was a postdoc. I thought that, and we don't know the association in reality. We don't know which point corresponds to which. That makes it very difficult. So the common wisdom was that first you solve the association and then you do the registration because it's easier, and then you do point-to-point matching. That felt wrong. I thought that no, you solve the problem and then the association will come out of the byproduct. And the way you can do it is that you think of each point cloud as a function. So if you grab all the functions, lift it to a function space, then the whole point cloud is just a surface. So now I have two surfaces and I want to align them. And the way you can do it in machine learning, there's a method on basically looks like kernel density estimation. I turn every point as a basis, and center a kernel around it, and then build a non-parametric surface out of it. And then my goal is that this will be lifted in a reproducing kernel Hilbert space, the vector space function is an inner product. So I have an inner product. I can just take the dot product of these two functions and maximize their correlation or minimize their distance. The T, the transform. T is the transformation. So the transformation sort of aligns functions. But this will be very difficult because what is the operator that will transform this function? Nobody wants to. No? First of all, or work with it, right? That's where we use the equivariant property that the transformation commutes with the input and output. Instead of computing the operator, these functions are equivariant, so sort of we use representation theory to define the linear action of the operator in the input space. That sort of makes it exactly like this, that sort of we're rotating and translating our point. So we do the kernel density estimation, and every geometric point wrapped around the kernel, say it's a Gaussian kernel, and it has a label. The label itself can be a tensor product of many features. It could be color, could be this segmentation of the scene, maybe the vector of probabilities of which category it belongs to. These days could be language features. As long as it's invariant, you can build this hierarchy of semantic representation using tensor products. Okay. And all this label sort of becomes weight for the kernel. And it could be intensity if you're working with grayscale image, it could be just a scalar. Okay, so, and then the takeaway was that we align functions, not discrete points. And that sort of optimization doesn't sort of try to get irritated to align every single point. Where in reality, when you scan the scene, because it's a discrete observation, if you move, there's no guarantee you observe the same point again. And then we solve this optimization, which also involved, you have to do sort of Riemannian optimization to get the rigid body. But it works really good. For example, on highway, it's challenging because if the vehicle is moving fast, you're leaving a lot of part of the scene behind. You scan here, and then the car is moving very fast. And there's a need for interpolation to connect these two frames. And when we just track frame to frame, we don't do global optimization to make it consistent. It works really good, and the symmetry again comes in the way we sort of define a transformation and use with the function. Now these days we try to do this within the neural network. We have some recent work because that allows us to scale it better with GPU. We implemented the classical version in CUDA. Took a lot of time, but that people don't want to look at CUDA code. All right, so and then we can extend it to multi-view. Forest scene, for example, is very tricky because everything is similar. Very difficult to associate which tree is which, but it works. It's, or you have this urban environment that you want to reconstruct the whole city. You can also do something like that. It's not real time.
So these problems, like in the forest scene, from that image, what are you extracting as output?
We use colored point cloud. There's a point cloud, range measurements, collection of points. Every one of them has color from cameras, RGBD camera.
And then you can, depending on where you are, you know where every feature is. So what is the
relatively? Every scan is relative to the sensor.
Yeah.
Then I move. The next scan is again relative to the sensor. I need to put them in a common reference frame. So otherwise, the map won't be consistent.
The output is like position vectors, location.
The output of the optimization
is
the rigid body transformation at every time step for the sensor.
I see. Thank you.
Which gives the trajectory. I need to estimate rotation as well, otherwise. Okay, so we do more. And we have some idea of the low volume visualization, also solve it globally. Robust to outliers. So one lesson is that the function space formulation seems to make any algorithm very robust to outliers and nodes. That's regardless of the problem. Because once it's a function, it becomes agnostic to the disturbance of the input. It's more about the disturbance in the domain. With a simple disturbance in the domain, sort of can capture a lot more than the complicated distribution in the input. Part of the mobile robotics like this is planned visual perception, sort of stuff that we teach students. And they do projects on stuff. Okay, so the hospital environments, there are a lot of reflections that makes it difficult to track. Underwater is also very difficult. When it's rainy, it's very difficult. This functional space gives a lot of robustness for coastal environment. Okay, so I think that lessons learned, those were specific problems, but I think this is across a range of engineering problems. It's that asymmetry is inherent to the theory, but not in the phenomena, are sort of unacceptable because there is a symmetric construction. The problem we should address it at the model level construction. And initially, it can sort of blow up and make your problem larger, but if you look carefully, often you can sort of reduce the size of the problem by symmetry, and that makes it efficient and generalizable. And a particular exciting direction is the Ghaffari representational technique, which is an active research area in my lab. And we need also new principle. Exciting direction is that this autonomy algorithm so far they've been memoryless. So the race is now we can have these large networks as memory, but the concept of memory itself is not well defined. How do you build a memory? That will be part of an intelligence system. That's it. With that, I have to answer any questions.
Questions? Thanks. Questions?
So, when you present study the dynamics, so have you ever compared with other system ID doing the traditional so that this as well as compared with the MLP and these methods. What about other here? System ID? You mean other non-neural network or other traditional? So if it's within neural network, you can replace MLP with other networks as well, but that's because that's the one that most people use, so to represent this. Outside of that, as long as it's optimization based, I think sort of you will get the same. At best, you will get the same results that you can do with MLP. It's because MLP at the end of the day, you're running an optimization on it. So just give you the best possible. If you pick one layer, you are fitting a linear system. Pick two, now you're fitting a nonlinear system. So it is system ID. You can think of it as system. It's just that the optimization framework is on GPU. Training is using gradient descent. We could use convex optimization, but the problem with those classical problems is that scalability. There's a limit how much data you can use, and those models, they don't get better as you increase the amount of data. Deep learning is the only learning paradigm that it gets better as you add data. So I agree, we could, but there's no pressure to do it from the machine learning community. They moved on.
For the trajectory prediction that you were talking about earlier, how sensitive would the prediction be on the type of motion itself? So the trajectories you were showing were like very stable, like it goes straight, then left, right, very stable trajectory.
And the estimation problem.
Yeah. What if the motion is extremely unstable or difficult to, or not difficult, but like it's very unstable, not very organized? So, for example, the Euler equations for motion. So I was thinking that, for the tennis racket theorem, where the motion is extremely unstable on one of the principal axes, how well would the prediction be for that type of motion compared to stable one?
That's a good point. So you should do the simulation program at tennis racket. And then
yeah.
Heading and then flips.
Yeah. So on one of the axes, the other two axes are stable. Yeah.
That sort of makes it almost like a hybrid system. It's not. Still continuous, but almost like a switching system, right?
I see.
But so we don't assume. So you're talking about state estimation or learning dynamics. Good.
I was thinking more on this. Yeah.
So we don't. On this one, we don't assume any particular motion pattern. We just read the accelerometer and gyroscope data. Now, what happens is that whatever movement you have, the accelerometer and gyroscope at a very high frequency will tell you how you're moving. That's not a concern. This could be a very fast movement, or drone can do aggressive maneuver. And these signals are at very high frequency. IMU works at 500 hertz to 1 kilohertz. It's not, I wouldn't say it's a particular point of concern, but it's important to, if it's very fast, it's also important to have good quality complementary measurement to correct, right? To your point, if it's going really, really fast, then maybe you have to record it at some point.
And what was the second thing? So I was
talking. That's fast as they could go.
I see.
Good. Ask them to go fast.
Yeah.
Yeah, but very, very high speed. I don't know, but within range of motion that vehicles move. For the learning dynamics, our current work is on learning hybrid systems. Then you have discrete continuous, and that makes it very challenging. That's a very good point. I'll tell my lab what the tennis racket. It's more interesting than the International Space Station.
No, actually, I learned about it when I saw a video on the space station where they, I think, flipped an object with like which has three different moment of inertia along the three principal axes, and on one of the around one of the axes was unstable. So then, yeah.
No, right. The dynamics could be unstable. We're just learning the current to predict. We're not controlling it, but yeah, it could be. The data we use is always stable.
Good presentation.
Quick question about the linear idea. So for that, like for input are the Lie group that are admitted under sort of dynamic system. Within the neurons, the activation functions are those the symmetry preserving operations associated with the Lie group. So are they specific to different problems? Do you need to design the neurons?
Specific to the group.
Yeah.
The filling form. Which for rotation, you can literally write it as a dot product of the vectors.
Right.
It has a different form for each matrix group, but it's something that you can find in the Googling as well. It's not a.
So is the essential idea like for different problems you find the group and the social operations and encode operations with these neurons?
Right. It's a sort of established math. But to your point, one limitation is that you need to fix the group, right? At the end of the day, this Ghaffari network will be Ghaffari to one fixed group. So so the broad direction is that you would want more than that. You want to handle a variety of maybe groups and so the more general structure. That is a good direction.
A follow-up question was like from what I learned about these spaces, sometimes the boundary conditions constraining the system destroys the Lie group that it can be admitted. Are these framework handling those conditions, or they are always treated free space sort of non-constrained?
It doesn't. We sort of we build it around the whole group, so we don't set any limits. But if there are constraints, you can sort of maybe add them, regularize it during training, during deployment. Just for learning the features, hard to say it's necessary. This will be encoded.
Yet the variables they're not a function of space. The notion of boundary conditions is different.
No, but the way you construct the Lie groups, you're considering you have the freedom to construct them in whatever. Sometimes the boundary condition destroys, you can extend it to positive infinity.
So the systems you consider are all of the form DDT. They are a dynamical thing, right? It's position, velocity, acceleration of a rigid body, isn't it? It's not a field variable, something that's a function of space that's also moving for that also.
No, it's fixed. So the basis space is the Lie group, and here the dynamics is very special. It's just evolving in that group. There's no constraint. I think the interesting part is that if you define your problem as a Lie algebra, your PDE, for example, you're going to have boundary value. Or to, for example, extend this to your PDE in the Lie algebra. That's not done. It's sort of doesn't come up if you're working with robot right now, but I think it's very useful if you want to predict fluid system or model environmental forces. But it is a significant harder problem. People tend to steer away from it.
People had looked at Lie groups in turbulence modeling several years ago. I remember when I was a postdoc at the Mobile Lab, I looked at it. Now, when you describe these things, I was wondering, just a general thought, if you look at the fluid equations in Lagrangian coordinates, I wonder if that, along with this kind of a description, because there it's the Lagrangian formulations like except it's a field variable.
There are some hard to read literature on Lie group based, fluid system.
Yeah. The Lie neuron also, I think, is something.
Lie group thermodynamics is also very interesting. Some interesting books.
Very good.
Connects to generative models.
Very good. Okay, we can talk offline, but we are over time. Thanks, Moni. Excellent. Excellent. Thank you.